there is this area I posted a video yesterday and a podcast yesterday. I don't know if you know about it, slope squatting in AI. Um, it's a recent way that AI introduces this malware into software development frameworks, because most times due to things we do like vibe coding, we ask AI to write these things for us. And some of this AI like ChatGPT, Claude, and Google Gemini, some of them may introduce this sort of hallucinations. So they hallucinate, and when they write out a package that doesn't exist, so by the time you running it, you discover those some of these packages don't exist. So now, how about when a fraudster or a hacker study these packages that don't exist and go about to trick them for the wrong reason, and quickly go to GitHub and put in these packages. So by the time they put in these packages, next time that the AI is writing it, it won't detect, it will include them as real package, but in other words, they are malwares. They are not packages that are existing. And immediately people start downloading it. You could imagine you willingly giving out your computer or your system or your database or your whole framework access for those hackers to do whatever they want to do with it. So it's actually a very dangerous trend right now. It's recent papers from 2025 I came across it. So I was actually thinking about how I could be able to work in this area, but in relating to healthcare. So I'm currently writing a proposal on it. To close this door because I have noisemakers in this house. Okay. So today, if you remember, we start the deep neural network. We talk about how it's been applied and where those things have been applied. So one of the the interesting area we want to look at today is convolutional neural network, and then the application in lung cancer detection. Now, there is a problem of lung cancer. It's one of the leading cause of death globally, and early detection is often a problem. It's not something that you could easily figure it out. So most of the time, you see experts, they struggle to detect these things at the early stages, and when it gets to advanced stage, it becomes quite complicated. And if you know the human biology, you will know that there are organs that are very, very crucial in your system that once they start getting affected, it affects your normal life and everything. The lungs, of course, we know how crucial it is in helping us to be able to exchange gases, oxygen, and breathe out carbon dioxide. We also have another organ like the heart, which helps in the circulations of blood. And then we have the liver and also the kidneys, even the intestine, the digestive system. So it's a very crucial system. So these systems are very, very important, that anything that affects them, affects the whole entire body of the human being. So you could imagine these things are something that we need to figure it out on time in order for us to be able to mitigate the risks and also the rate of death globally. So most of the time, the experts or radiologists, they usually relied on CT scan analysis in order for them to be able to come up with a conclusion if there is a cancer, or maybe if it's cancerous or benign. turmoil and all that, So it's actually time consuming, Could imagine when you have thousands or millions of these CT scans for the radiologist to do that. And when it's an emergency, like we saw in during the COVID uh, period, there was a breakdown of in the healthcare system. We saw a lot of issues because then so many emergencies and people, I remember there was really, and it came to a point that um, students in medical field, like in let's say 400 level, 500 level, have to be, take hurried up into the field to go and save lives, because of the shortage in the manpower. So there was a lot of issues, are there that period of time. So it's usually time consuming when these radiologists have to go through these things one at a time. Also, it's prone to inter-observers variability. While radiology, there was this article I read one time that there was this particular area of health. I can't really remember which particularly, that they have to fly all the way from the US to India because the expert that does it lives in India. So they have to take those things each time to go and meet him in India for him to do the interpretation for them. Or sometimes he will have to fly to the US to do the interpretation for them because globally he was like the only guy that had experts in doing that particular interpretation. So that kind of issues, you can imagine how busy that kind of person could be. And probably if you have three or four of them, sometimes the what one person is observing may not be the same with what another person is observing. So there could be that variability in the interpretation of this CT scan results. So it's usually difficult to scale, especially in low resolution or rural setting. So you could imagine if even in the city you are having issues, then how about somebody in rural areas? It could be very, very challenging for them. So how can AI now help? Is it possible for us to use AI to solve this kind of problem? Because you could see it's quite an issue, not just for lung cancer. There are so many other areas, like I said, relating to some of the vital organs like heart, liver, kidneys, and even the digestive, like colon cancer and all that. So some of these areas need expertise, and sometimes this expertise is really, really lacking. Now, imagine like in Africa, Nigeria, precisely where we are beginning to have a lot of shortage of these experts migrating in search of greener pastures. Now we are having doctors that they are really, really having a lot of shortage of them in Nigeria right now, and even nurses. So that kind of situation where we have our experts migrating in droves, it's going to be a very big problem when this kind of emergencies comes up. Who would be able to help us, to do this kind of interpretations in the absence of these radiologists, And I could tell you for free, most of the hospitals I have visited here in Europe, most of them are, they are mostly experts from Nigeria, Ghana, and some of the developing countries. You see them working here. So that really tells you we are losing a lot of these experts to this first world countries. And this is not a good thing for us. So how do we help people back at home, even if you are in the diaspora? How can AI be able to help, to mitigate these things, to be able to reduce the burden, the healthcare burden, in the system over there in Nigeria? So one of it is we have lately witnessed a rise in artificial intelligence in area of medical image analysis, and particularly methods like convolutional deep neural networks, offered a very promising solution for automating and improving the accuracies of detecting this lung cancer. So it means we can train the AI to be able to recognize what is a lung cancer and what is a normal cancer. And then that we could be able to make detection easy for the radiologist. So sometimes we don't have to constrain the radiologists to do that because there are other past images that they must have observed. It's just for us to train the AI to know what is this image and what is not. However, building an effective AI model in this space involved a lot of challenges. One of it is, I don't think I mentioned that, but data privacy. Most of the time in the medical domain, one of the problems we really struggle with is data privacy, data access. You see that when it comes to getting patients' data like that, it's not really easy. There is a lot of ethical consideration, and that could actually be a problem. But when you be able to sort that kind of problems out by maybe relating with the ethical committee, they review your proposal and see that it's something that actually could help, you also going to face problem like handling and processing the medical images. Because some of these images, remember, they are in form of CT scan. So you need to make them to actually be in that computer resolution format that you can be able to feed the convolutional neural network pipeline. Now, designing and training a robust CNN architecture is also a challenge. Remember, I told you guys last time that how do you know when it's the right layers to stack? Do you make it so deep? Like how deep do you have to make it? Do you have to make it 4, 5, and so on and so forth? So this kind of challenges. Another thing is the evaluation metrics, which kind of evaluation metrics you have to use, because there are situations you will be faced with a lot of imbalances in the data, and then accuracy can't be trusted in that kind of situation. So you have to fall back to other matrices like the F1 measures and all that to be able to work in that kind of complex setting. And then addressing issues like overfitting and data imbalances, and limited label data could also be a challenge. Now, if you know the AI, and you must have heard me say it countless times that AI is data hungry. Most of the model do well when we have lots of data that we could be able to feed it. The more the data, the better the model perform because it will learn so many patterns and be able to generalize better. So the goal of this hands-on section is we want to build and train a convolutional neural network to classify long CT scan images as either cancerous or normal. So it's either malignant or benign, It's and not just because in this case, actually we have 3 types. So we are not dealing with 2 classes, but a multi-class problem. So take note of that. We want to pre-process the medical images in, you have to make sure we resize it, normalize it, and also augment it. And then also one of the objectives is we want to define and train the CNN architecture that will be able to give us an optimal performance. And also we want to evaluate the model performance metrics in form of the either what do we call it? Um, Accuracy, recall, precision, confusion matrix. Could be any of this matrix or depend on what we want. And sometimes we're also interested in the losses. Remember the loss function I told you guys when we are coming back via gradient descent. Now, one of the motivation why we really want to contribute in this area is because in the early stage of this lung cancer, it's very difficult for you to detect it. Most people are detected when it has gotten to the late stages. So there is an importance of detecting this kind of cancer early. So the right treatment could be administered to this patient. Also, the use of CT scan to identify this kind of anomalies is quite crucial because that's what would help us to be able to see through these hidden layers in the body. Um, why CNN are ideal because it's used for image and object classification or detection, So the first step is to pre-process the data. That means we'll be needing tools like the Google Colab because your computer may not be able to have the capacity to train the new deep neural network. And I will talk about the Google Colab in a minute. We will also need things like NumPy. Of course, the NumPy help us to handle things that has to do with the data structure and all that, matrix manipulations that we do. And we talk about pandas and OpenCV and Peel. These are all packages we will be needing. I think we'll need other packages like TensorFlow, Keras, and all that. They are special packages that we use for this deep neural network. And then the data set we are going to be using is actually a data from Kaggle, and it has three classes of cancer that we're going to be looking at. But generally, we are looking at cancerous versus non-cancerous. Even though it's three classes, we have the normal and the other two types of lung cancer. And the first step is to gather this data, import it successfully, read this image, and convert them to the sort of array, and then be able to do these labels and all that. Like I said, it's three classes, not two. And so the data processing would involve us to resize them, sometimes around 2.4, 2.5, depending on the kind of size we want. Sometimes we could use 64 and all that. Then normalize the pixel values, and then we have that training testing, just like in the normal traditional neural network. Remember, we have the training testing split, and then also to do the pre-processing. So remember the architecture, when you have the image data, you send it to the convolutional layers where you do all the sampling. Either you reduce the sampling by resizing and then doing some sort of transformation, flattening it, and then at the end of the day, do the convolutional layer, also help you to do the max pooling and all that. So you know of this layer from the theory part of the class. And if you have not followed that, if you have not watched that class, please kindly go back to those videos on our YouTube channel and watch them. Then you can be able to catch up with this step where we are. And then another thing we want is to do the model evaluation, and then by fitting the model. And remember, because sometimes we really want to minimize the space, the computational space. So most times we feed the model in batches and epoch so that we can be able to, have that ability to process everything. And then we will use the validation splits to be able to test that the 20% we have set aside, we will test to see what the model have learned. And we will also implement the early stopping signal. We call it a callback. That will help us to, once we attain a certain threshold, we will tell the model to stop the training and go ahead. Especially maybe if you have gotten to maybe 90%, 99%, you will just tell it, okay, stop. You have learned enough, things like that. So we would display the classification results, which could be in form of accuracy, confusion matrix, ROC calls, precision recall, just like we do in our previous classes. So I think those are the few slides that I prepared for this class today. So I believe you can also see my screen. Can you see my screen?
Yes.
Okay.
Yes,
So
yes.
great. So I think what we are going to do now, if you have I hope you all have a Gmail. If you have your Gmail, certainly you have Google Colab. So the Google
Okay, it
Colab.
means that the neural network, we cannot train it on our system or something. On our
You can train it on your system, but the thing is, most times it depends on how heavy the layers are. If you are stacking the layers, you are likely not going to be able to, it will exhaust your RAM. So you will need, that's why most times we need cloud infrastructures sometimes, or high computing resource. I remember during my PhD, we have this clusters that we use for this kind of tasks. So most times I don't do these things using my normal this thing. So I think then I have this Jupyter Lab. Now I wouldn't have access, of course, because I've graduated. But then I can't remember it again. I think Jupyter Lab for remote computing. So I did. Yeah, I think this is an article on how you could be able to launch the Jupyter Lab. I could send it to you guys because then what I do, I had this Jupyter Lab. Then I use, if I have to use a Jupyter Notebook, and if you write the Python script, you could write it and run it, just submit the job. I think I would have to teach you guys, especially on cloud computing. Maybe I think it should have make a lot of sense. So you guys could see how you can be able to do that. But again, it will make sense if you are having access to a cloud infrastructure, then I could show you guys how to do that, how you could. But I think you can still be able to use one of those Google Studio to do that, or AWS, Amazon. I think EC2, AWS, Amazon should be, there is a free version. I'll check if there is. Then we could arrange one of the class where you guys will see how to train your models on cloud, so that instead of stressing your traditional computing resource, or your RAM, it's better you do that. But again, if you have a system like Mac and Linux, I think the computing resource on those platforms should be quite high. So I think you can still be able to do that. So depend on the space you have. But like my system here, I have two. One of it is Mac. I've not tried to train on Mac, but I'll try to see. So, although I have access to the cloud infrastructure of my university, but I haven't tried. Maybe I'll try to see how it does if you can. But generally, I wouldn't advise you to use your traditional computing resource. Okay. So if you type on your system on Google Colab, you'll be able to see what Google Colab means. It's actually gives you that computing platform. they say Google Colab or Collaboratory allows you to write and execute Python in your browser with zero configuration required, access to GPU free of charge, easy sharing. Whether you are a student, a data science account, then you can be able to run it. So whatsoever you want, you can, you can be able to do that. All right. So you can see so many examples. This is for data science. This is how you're running it. They say Google Colab execute good code on Google Cloud Service, meaning you can leverage the power of Google hardware, including GPU and TPUs, regardless of the power of your machine. All you need is a browser. For example, if you find yourself waiting for Panda code to finish running and you want to go faster, you can switch to a GPU runtime and use library like Rapid Code that provide you with zero coding changes acceleration. So you could see even on things like machine learning with Google Colab, you can import image dataset, train it. So as I was saying, the dataset we are using is about 25,000 histopathological images with 5 classes, which is around 768 times 768 pixels in size. They are all JPEG file formats. And the images were generated from an original sample of HIPAA, HIPAA compliant and validated sources consisting of about 750 total images of lung tissues, 250 benign lung tissue, 250 adenocarcinoma, and 250 lung squamous cell carcinoma, and 500 total images of column tissue, 250 benign column tissue, 250 adenocarcinoma, and augmented to about 225,000 using the augmentator package. So what they did was the original was around 750 total images for the lung cancer, and then 500 images for the column cancer. So they kind of randomly augment it and made it to be around that 25,000. So, but we will focus on just the lung cancer. That's what we want to focus, which has 3 classes. That's the lung benign tissue, the lung adenocarcinoma, and the lung squamous cell carcinoma. So that's the 3 distinct we want to focus on. So this is where the data resides for the column images. You have the data set here. For the lungs, you also have the directory here where they save all the data here. So Kaggle, of course, I've told you guys a bit about Kaggle, where I told you last time that most of the time you would see a lot of data set that is so many organizations, individuals, for competitions and all that. You always see people putting on data on Kaggle. So it's a very good platform where you could get data and you could interact with data, and you could also see code that other experts have worked on, and you can also be able to pick some of those codes and work with. So it is on this basis we will be looking at those images that have already been done, and then we will build our analysis from there, using that images from the Kaggle. So let's begin. So the first thing we are going to do, you will have to create. So in order for you to open, so let's say this is when you come to your email, So this is actually the email from our Data Edge Academy that we are using. So if you increase it, you could see when you come to your email, your normal Gmail, you clicked on this buttons here, you will likely see the drive here. So most of your scripts, you will be saving them in this drives here, okay? This is where you'll be saving them. So let's say I've opened the drive, so I've opened the drive, so there is a folder here. So there is a folder here that I called Google Colab notebooks, where you will see I have these different notebooks that I've opened. So it's from this place here that we create a new notebook. So most of the time you could, and then when I sent you the script, you can also be able to upload it inside the notebook. So if you want to upload to work with it, you will come to this place, not new, and then you see this file upload. You click the file upload. Of course, you see it will take you to where the script is. You will click at it and then you upload it, and you'll see it to get upload or something. And then once it upload, you can be able to just click open to your let's say that where the file is in your download, for example. You can click it and then you upload it, to your, but I think we are using IPython, so most times I think it will likely be in notebook format. Depend on the format it is, but you always have option in IPython or notebook format. So once you upload it, you would see something like this. The way to display, if it is in Jupyter Notebook, you likely see each cells, and then you can work with it. So for this class, let's create a new notebook, for example. So you can see a new notebook here. So once you click on the new notebook to create a new notebook for you, so it has created a new notebook for us, and then you see. So if you hosting it on the drive, and the drive, if I'm not mistaken, it's not much like that we had, but I think we can check the drive to see how many. So we have around 15 GB, so not much, but again, it's fine. We can use that. I tried to make sure I use a shallow network. I didn't really make it deep, so I think it will be able to do. So what we are going to do, the first thing is for us to import the libraries that we need. So you import the library, all the libraries that you need. Now, the good thing about the Google Colab is that you won't have to, it's not all the live packages you have to do the installations like we were doing on the Jupyter Notebook, So likely you just, you don't have to disturb yourself with some of them. But again, even if you have to install, it's going to be that the same way we were installing with this thing. So most of the traditional packages, you will likely see them, they have already been installed. So we just need to run this to see, and you can see, so it has run. Once you see this good here, it shows it's running fine. So we have imported the library. So the next thing is we now have to do the data extraction phase. So in the data extraction phase now, we need to call the data from Kaggle and save it. But before we do that, we have to put it in a location. So we want to put it in the location of our drive. remember we are here we have our drive here, which is my drive. So we need to call the data to download. But if you have already downloaded the data to your system, you just need to add the data to the location you want. So let's say if we want the data here, we just come to a new, then file upload. Then if it's a folder, you will just upload the folder. You understand? But if it's a file, you can upload the file. So any of the option that you click, you'll be able to work with it. So in our own case now, we need to upload, we need to connect it. So, but for you to connect, you have to give permission so it will be able to link your drive with where the date, because that's where you want to save the data. So we are linking the drive now. So, but you have to do all this, you have to give it permission so it will be able to do that. So again, you see, once it's finished running, it will tell you it's run successfully. So yeah, so the Google Drive has now been mounted successfully. So again, you create a cell. So each time, if you are writing a text, you click on this text. If it's a code, you click on the code here. Okay. So the next thing is we need to remember we said we have to give the data in form of badges because we need to reduce the GPU memory so we don't overwhelm it. So what we need is to make sure we reduce the sizes also. Remember the original image that those guys had, it's around 750 something. So, but we want to downsize it to around 128. And then we also want to make sure we give the batches, we put it in batches so we don't push all the data at once. Then the test train split, remember, is 80-20. So that's why you see we put this 0.2 here. And then the epoch, we have 10. Okay. So remember the reason we are doing all that again.
So what's the role of the batch size again?
So the batch size is to help us to minimize the memory for the GPU, because if we give remember we have 25,000. Imagine giving, let's say in the training set, if you take away from 80, I think you have around 22,000 for the training. So imagine giving all the 22,000 to the model at once. It will overwhelm the system. If you don't have a lot of memory, it will crash. If you don't have, so we don't want that to crash. So we now give it in batch. Remember for National Youth Service, where they will say batch A, batch B, because if all the batch go at the same time, the camp will be congested. So that's what we are doing in real time. We just give it in batches. So that way it doesn't feed everything at the same time. So, but for us to be able to do this in Kaggle, we will need to install the Kaggle this thing here. So I think so if you come to the Kaggle where the image is, you will see this API for the Kaggle where you could be able to copy to be able to import the image here. So you need to copy this, and then if you copy this, you will now come to where this thing is. So that's what we did here. We're going to import it. So we copy and then we paste it here. So this will now give us the API to be able to call the folder where the image is here in Kaggle here. When you get to where the data is on this download here, when you click it, it will likely show you the API where you can be able to copy the data. But alternatively, if it doesn't work, you can be able to download it. You can see the full data set is around 2 gigabyte GB, so it's quite big. So if you don't want to use the API, you could just download it to your system and then you import it to your Colab drive before you can now be able to run. So, but I think for me, I prefer to call it directly from the Kaggle source here. So once you run this, so now it's going to put, so it has called it into our system. So now we already have the part working successfully. So the next thing we are going to do is to we want to do some sort of, we want to now check where the image is in the folder that we just called. So let's take a look at where these images are. Okay, so the images are actually stored in this folder in the in the path. So now we can be able to, because they are image, so we need, since we are dealing with image, the PIL is helping us to be able to read the image files, and we can be able to open them using that same img.show. So the img here, you could see we say image.open the image path. So now we can be able to look into the image. So now let's try to look at the kind of images we have in brief. So again, we add a folder, and then let's see what happens. So if you run this again, this would display the images for us. Good. So now you can see the images we have. You can now see how the images look like. So this is image for long ACA. That you remember from here, we when you looked at the description, yeah. So when you looked at it, we had the long adenocarcinoma or so. So this is how it looks like for them. You can see how those ones looks like. And then there is also the another category that we call squamous cell carcinoma. So the squamous cell carcinoma also look like this. So you can see they had a bit of different. Then the normal lung look like this. Anyway,
Okay.
so the next thing, you can see how the both these different categories, you could actually see we did have some differences on how the images look like. You can clearly see they are not the same. This is the normal lung cancer. Can you see? Oh, sorry, the normal lungs. Sorry, the normal lungs look like this, but you can clearly see the affected ones. You can see how they appear to look like. So clearly, we did had a very we did have quite differences between them. Okay, so very good. So now let's so the next thing we want to do is we need to use the image data generator for data loading and augmentation. Now we need to rescale the data, because if do that, we can't be able to work with it. So rescaling the data means we need to first normalize, and then we need to also do some sort of rotation, the width of the sheets, the height, the horizontal flips. We need to just do some sort of customizations to the data. So that's what this part of the code here. Okay, let me see. Yeah. So once you put this and you run it, Okay, so once we run this, we are going to we have done that for the training. So the next thing we need to do for the training, the resizing and the batches for the training before we finally go to the model architecture. So again, we run this. So it may take a bit of time for the data generation to go across all of them. But also while it's running, let's do also for the validation set, which is the 20% we set apart. And then we can look at, okay, so it has run. So let's do for the validation set to see what we are going to have while it's running. So the next thing, let's define the model architecture that we want to use. So let's see what happens. So remember the model architecture, like I said, you're stacking them. So each of this, those layers that we have, you have different layers. So that's what we are having here. So because remember we are feeding it in batches, so we talk about the sequential because it has to go in batches. So we have first we have 3233, which is the first batch. Then there is the max pooling layer. Remember we talked about the max pooling layer. Then we are putting it remember we have also normalized it earlier on. So which is what we do. So this is first layer, this is second layer. So you could see this one is 32, this is 64, this is 128. So this is 1, 2, 3, then the fourth layer. So again, we could have stacked the layers depend on what we want, but I think I just wanted to keep this simple because I felt we shouldn't really bore ourselves with so much layers because of time, since this is just teaching. But you are free to explore other architectures to see how it looks like. So the model is not much, we just define them. Then let's still go again. We're still in the model architecture. Let's look at the summary of the model architecture we define and see how it's going to look like. So let me zoom out a bit. So you could see this talk about the layer, the output shape, and the parameter. So the curve V2D, which is the first layer, it's 128, then 32. That means it has 896 parameters. Then the max pooling layer, for the first layer, we have 64, 64, 32. These are 0 parameter. Then the batch normalization, 64, 64, 32, it has 128 parameters. The first convolutional layer, when you open it, you have around 18,496 parameters. Can you see how it's increasing? Then if you continue that way until when you come to the flattened layer, the dense layer, you can see we have 4,194,432. Now, can you see how big this is for the parameters? Can you see this is quite big? Now, in total, you have 4,289,475. Then the trainable parameters is 4,288,771. And non-trainable parameters are 704. Now, look at the space that the model is taking. By the time you add this, I think you are going to have around 33 megabytes. Now, imagine when you have so many of these layers stacked, the parameters could go into billions, go into trillions. So now imagine things like ChatGPT that has a lot of layers. So the more you stack these layers, the more you need this computing resource. Now imagine as humans, how would you be able to process this millions of parameters? You see, it's kind of practically impossible. So that's what these deep neural networks do. So the more you stack the layers, the more it becomes complex. So you could see just this few 4 layers that we are having, we're already having 4 million parameters. So the next thing we are going to do, we want to compile the model. So we have defined the parameters, we have structured the data the way we want it. So the first thing
So
is model
what's the significance of the numbers of layers?
is processed because each layer that it goes, remember, if every layer that it goes, it scans the data. So one of it, some of the layer will focus on small let's look at the image, for example. So there are layers that will focus on maybe this black images here. There are layers that will focus on this ones, the white one. There are layers that will be looking at this kind of lines. There are layers, so they are, as you stack the layers, that's how it distributes the job of recognitions. And each of these layers they will diligently do them by dividing them into tiny pixels. So once they divide them into tiny pixels, they will now allocate numbers for them, like their matrix. So each of these, so let's say maybe the first layer will roughly split them into, let's say 1, 2, 3, 4. Then each of these 1, 2, 3, 4 will move to the next layer. It will again split them. So each layer will continue to focus on tiny nitty-gritties in that image. By the time it has completely studied that image, it will now start adding up what it has learned or regurgitating what it has learned. That's what we mean by flattening that layer before we come to the output. So by the time you flattened the layer, you bring in everything you have learned. Now, imagine doing it for thousands or millions of these images. It's going to be crazy because it's much. So the more you stack the layer, the more it picks up things that were omitted by the previous layer.
So how do you know the number of layers that is most effective or efficient or as enough for a particular data?
Yeah, I think there are approaches that you can be able to know. I think one of it is by the number of images you have, how many data sites you have in determining, because the more you have a lot of data, the more accurate you are to learn a lot of things. And then secondly, I think you could use things like kind of like a cross-validation sort of approach to determine them. Like some sort of grid search, it will automatically pick which of them you use. Then again, you could use pre-trained models that somebody have already trained. You could adapt them, and then you modify them appropriately to your work. So it means that I mustn't. Well, and that's the beauty of this AI data science stuff. Most of the time, I don't need to start something from scratch. I just need to look at what another person have done, and then I can adapt what they have done to what I'm doing. Now, that's why I told you guys last time that this is the beauty of literature review. That's why anytime you are doing something, try to look at literature to see what is available out there. What have others done that you can build upon? So like this lung cancer class that you guys are doing, I just take a look at what others have done, and then I adapt their code and modify it for our class. So you don't have to copy the person verbatim. but you can be able to tweak what they have done too, because every problem is unique. There are no one fit size all solution. So if I'm working on let's say object recognition, for example, I just need to look at what other things that people have done on object recognition. There are countless of them that are online. So once I see it, I will now be able to look at the architecture. And then from the literature, I will definitely be able to recognize the gaps. And then I could bring in what I can do to fill in that gap that those people were not able to do. That's why it makes sense when you explore literature. So if that person used, for example, 5 layers, I mustn't have to use 5 layers, but it will make sense if I start from the 5 layers that person have used to see the kind of results I'll have. So when I have results for 5 layers, the next thing I'll say, okay, probably this person used 5 layers and the validation set gives him 85. Why not maybe I use 4 layers and use another modification that this other person has recommended from his own work? So why don't you try that with what that person did and what this person does? You match them, you'll be able to maybe move to your own to 86 or 87. So that literature will give you that proud information to build upon what other people have done. So that's one good thing about science. Most times you are not working in isolation. There are things that other people have done. That's why I told you guys last time that anytime you have an AI data science problem, the first thing that should come to your mind is the data. How is the data? How will I be able to lay my hands on the data? Because I could tell you a lot of things that are in my head right now. So many business models, so many interesting things that I could tell you, and you'll be excited. But at the end of the day, the data becomes the big cat in the room. Like I told some persons last time, and they were laughing that there is a story about the cat, that was giving the mouse in the neighborhood problem. So each time the mouse wants to go for expedition, the cat will just come and, close the case. So one day, the whole mouse in the neighborhood held a meeting. So when they held the meeting, a very young mouse now came up and said, why not when the cat is sleeping, we get a bell and tie it around the neck of the cat. By so doing, we wouldn't have to be scared, because each time the cat is coming, the bell will be ringing, and we would know that the cat is coming and we'll go and hide. So the whole mouse congregation clapped for him, and they're like, wow, this is a brilliant idea. But then there was this old mouse. He was looking at them from the corner, and he said, my children, you have spoken well, and I like this idea because it's going to save us. But now, which among you will volunteer to go and build the cat when he's sleeping? And now that was how everybody kept their hands. Nobody raised his hands. And that was how the meeting broke. And everybody went home and they were very sad because nobody is willing to build a cat. So why did I bring that story? We can always talk about beautiful ideas that we want AI to solve for us. We'll go ahead to talk about some nice solutions of how AI could do wonders. But if you don't have data, these solutions can't come to life because AI fuel its data. Just like how your car cannot drive itself except you put petrol or gas, that's how AI can't function without having data. So the chat GPT you see today, the Claude, Google Jamming, and all that, all works on data. They train them on all the data we have so far produced on the internet, and it's now leveraging on that to be able to give us solutions. So the same thing when you are thinking about your problems, always think about the data, structure the data to the right framework, then you could deploy the AI to solve the problem for you. Okay? So I think that's I hope I answered your question. Monday, I say I hope I answered your question.
Yeah. Sorry, I
Okay.
didn't know I was mute. Yeah.
Okay. Okay. So the next thing we need to do is to customize the. I'm sorry, we need to compile the model. So during the model compilation, so we have model.compile. So when you have already written the model, you have already do the architecture of the model, you need to compile it. So that's what we just do. And then in this compilation, we and also when you look at the problem, it's not really much. It's more like the data is kind of balanced. From what we actually know from the Kaggle here, we could see it's not really an imbalanced problem. So we feel free to use the accuracy for it. And then the next thing we are going to do sort of a callback. Remember, the callback is also to help us to stop the training if we get 90. If you like, you can tweak it to 95. If you like, you can even say 99. But for me, let me just stop at 90. But it's going to also, I think the model training will take time. Also, even though probably like 10 minutes or 20 thereabouts. But let's see. I think it did take time when I ran it earlier. So now it's running. So we remember we have 10 epoch. So you can see it's going to take time because we have 1,500, and this is so it's kind of, but now what I want you to focus on, you could be looking at the losses and also be looking at the accuracy. So you see at you tell the student what is blue and what is green. So each time you are showing the student, you're telling it and say, this is green, this is blue, this is green, this is blue, this is green, this is blue. So to a large extent, the student is re-echoing what you have shown him, isn't it? So, but the validation now, we hide the answers, and then we now tell the model and say, now show me what is green, show me what is blue, show me what is green, show me what is blue. Yeah. So to a large extent, the student and then there are situations where you now show the student an indigo or a red, and probably during training the student didn't even see green, he didn't see red and indigo. He just know that this is blue, this is green. So by the time the student now sees it, the student now of course the student will not tell you didn't train him. The student will now make up his own and now tell you and say, this is green, even though it is red. You understand? So that's what the machine learning. That's why we said give it a lot of data during training, so that the model will be confident while making decisions during validation or testing. Because if you don't give if you don't give it a lots of information, he may not see them. And that's why I tell people that I belong to a large extent. I'm in this school of thought where I think the training testing should be to a large extent even less than, you could even keep it 90-10, because the testing set is it's just a one-time thing. We are using it to validate. So the training is where the model should learn as much as possible. So if you don't have a lot of data, I would say you can even do 85-15 or 90-10. where you keep 90 for training, 10 for the validation. Because I see some people doing 70-30. That 70-30, you are really starving the training, that information. Because the testing, you don't need much of it. Because if you even deploy this thing, the model in the field, sometimes it's one patient you are going to have at a time. So if I'm having one patient at a time, why should I be bothering myself to have a lot of no? It doesn't make sense. So it's better I keep a small portion for the testing, even if it's 5%. I've even seen where people keep 99 for training and just 1% they use it for testing. Yeah. And it makes sense because I don't see any reason why I should keep a lot of those things for the testing. Even you as a student, what do you use after exam? What do you use it for? Do you
Is there no case
understand?
that the test, will it not be a case of after teaching me and then you just came and asked me 1+1 and I say 2,
Yes,
it looks like 100%, but whereas you didn't really test me on more complex
yes,
data,
yes.
will it not be have any other, if any side effect or something,
No,
any drawback?
it does have, but you see, in this case, we want our model to really do well when it go out there, because I won't be out there to just like imagine your model. Just look at it like when you are preparing your students for, let's say, quiz competition or debate with another school out there, our student out there. So you want the students to learn as much as, even though I'm going to test them, but I want them to learn so many of those things because I don't know the kind of question they will be asked when they go out there in the field. So in that kind of situation, the questions I'm supposed to have teach them, I now hide it. I'm not doing them a favor when they get to the field, because there now when they get uh to meet other complexities that they have never come across before, they will likely perform woefully, even though I have teach them and prepare them. But because I hide those things and said, no, let me keep it so that I'm going to test them to see if they really learn. Instead of me to do that, let me spend more time teaching them, so that by the time I spend more time teaching them, by that time, even when we bring in any kind of question, I am that confident that my students will pass. They will do well because I have taught them very well. So that's the notion me I see about it. And that's why I say it's a school of thought. Other people can disagree and say, no, they want to keep it, so they, just like you are saying, you want to be sure that. But again, if you are looking at it that you want to really deploy your model to a world that is full of uncertainty, then it makes sense if you teach the model with as much data as it can during the training. So that way, when the model go out there in the field, it's very confident that what it's going to meet, it will not just guess it wrong or guess it right. Because the real world is really crazy. Like the uncertainty is not, it's not something you could predict easily. So your model was trained more in a controlled environment. So what now happen when it go out there to meet a change scenario? That there's this text. I hope I could lay my hand on that textbook. We call it um trying to look for the right word for it. Predictive predictive model performance or something. No, predictive confident interval or something. Not interval. There is a particular word we call it. It's not interval, but I forgotten that. But it's something that has to do with predictive confidence. Some I can't remember, but you can still feel free to call it interval, but it's not interval too. What that word means is that when you deploy your model, there is most times a distribution shift. And that distribution shift is because of the uncertainty in the real world. So when there is a distribution shift, most of the model perform bad. So the model begins to misbehave. And a good example that I read from that article was the case of a drought. They trained this model for water board or something because they needed to manage to ration the water distribution during summer seasons where there is a lot of drought cases. So they need to make sure the dam, they looked at the level of water so they could be able to make sure they plant. So later on, because of climate change, they noticed with time the model was not doing well again. So they need to come back to look at what happened. So that's where they discovered that because of the distribution shift, even though the model was trained very well, but the changes that happen over time makes the model not to perform how it ought to perform. So that's one of the things you get when you train the model. That's why it's recommended, even though you deploy the model in the wild, always come back to retrain the model because it may not be what you see. Like Kenyans will say, it's not always Uhuru. So it's not always Uhuru. So you just have to always come back to make sure you retrain it so that you don't get so confident in giving you nonsense. So that predictive interval helps you to be able to detect in time when the model is beginning to shift and giving you wrong thing. So immediately you notice that, you can quickly come back and retrain your model with a new data set that you now have. So that way you could keep it. And it's one of the danger of AI. Human beings shouldn't be so confident
Yeah,
in
validation
AI.
accuracy is 90%.
Yes. So now I think we had around it has reached 90%. It end with around 89 point something. So the validation here, okay, yeah, validation accuracy was 93. Nice. The learning rate was also around 0.001. So this is it. So now the next thing we are going to do now, let's check on the validation and then we do the interpretation and we wrap up. You can see we have exhausted our time actually. But so this is one of the things about these deep neural networks. And in fact, I have to look at it to make sure I run it on my own, looked at the timing and cut down so many things so that we don't have to spend the whole of today expecting the result. So otherwise, we could have been wasting a lot of time. And I do want us to, because doing this kind of classes is just to show you guys how these things work. And then on your own, you could try out more complex things. Okay, so the validation has run. So let's see what we have. So the classification report, you could see we have around precision of 90 for lung cancer, this other one, the first case. The normal case, we have around 98 for precision, recall, F1 score. For the long sec, we have around 94, 90, 92. So they both actually detect it very well. So we have accuracy of 94. So it will make sense if we looked at the confusion matrix, because I always say I'm a fan of confusion matrix. That's where I always look at how the accuracy, that's where I really looked at what was classified right and what was not done right and what was done wrong, stuff like that. So the confusion matrix usually give me the true picture of the ones I missed out and the ones I got right. But sometimes the accuracy could be deceptive, especially when you have imbalance. So the confusion matrix gives you a good picture of it. But sometimes when the confusion matrix is more than 2, 3 classes, it doesn't make sense because now you have lots of backs, ups and downs, looking at trying to understand the diagonals. Because when it's 2 or 3, you can easily look at the diagonal and know what was done right. So you can see for the first one, it only missed classify 15 and 64 for this one. And it did make sense because of course these cancers can be it said they are normal. Just 15 cases it said they are normal, but in real sense, they are actually cancerous. So that actually makes sense. Then it did say 64 cases were belonging to the second cancer group, even though they belong to the first cancer group. But that's very small when you look at this percentage that were missed out. But 921 cases were gotten right out of 1,000. So it means the chances of making errors will not. Then for the normal cancer, you could see it didn't even have any, it got all the cases right. It didn't miss anything. Then for the third cancer, it got 891 correctly. So it was only 199 that it misclassified as the first cancer. And it didn't even misclassify any of the normal one, which makes sense because sometimes it's better we say that the patient has a cancer and even if it's not that very cancer that they have, than for us to say they are normal when they have cancer. You see, so these are some of the things you'll be looking at in the model when you have the model. You weigh the risks, and it's this kind of confusion matrix that really gives you the true picture because somebody sees that 91, 90, 98, and all that 94, you say, my model is good. But sometimes when you look at it in detail, you can be able to give it a good interpretation, and then it helps you to see if you have to tweak the model or you are okay with it. So I think with this, we have come to the end of convolutional neural network. You can also try out other. I could see if I can add other example like the cat and is it cat and dog detection for object detection. Let me see if I could add it before sending you guys the script so that you guys can also see for object detection. Then next week, I think we will go to recurrent neural network.